Okay. So, thank you very much. I will talk about forward angle electron spectroscopy in high ion atom collisions. I come from GSI in Darmstadt. That's a heavy ion accelerator facility, and we can study ion atom collisions with projectiles ions up to bare uranium. So, in my case, we used uranium-88 plus ions, so beryllium-like 4-electron system, colliding with a nitrogen target. And our aim was to look at electrons that are emitted, so-called cusp electrons. And there are 3 processes where these electrons can be observed. In this system, the electron can either be ionized from the projectile. That's what we call electron loss to continuum. Then the electron can be ionized from the target and be captured into the continuum of the projectile. That's electron capture to continuum. These 2 processes have been known for many years, but they have not been studied extensively for really heavy, highly charged ions. And since we have this heavy ions, there's a 3rd channel which was observed, which is the radiant electron capture to continuum. The electron is captured from the target into the continuum of the projectile while emitting a photon. And as we will see later, this is directly a Bremsstrahlung photon, but in inverse kinematics. So how do we observe these electrons? We use the experimental storage ring at GSI. It's a heavy ion storage ring with a circumference of 108 meters. The projectile ions are injected at 90 MeV over U. That's roughly 40% speed of light. We use electron cooling to have a really high quality beam. And as detectors, we have detectors for ions that have lost 1 electron, for ions that have captured 1 electron. And then we have a gas jet target where the ions are intersected. And around this interaction point, we have X-rays detectors to observe the X-rays. And for this spectrometer, for this experiment, we built a dedicated electron spectrometer to observe the electrons that are emitted into the forward direction. So more closely, it looks like this. The beam is coming from the left. The gas jet target is coming from the top to the bottom, and the electrons are emitted into forward direction. Then we have 2 dipole magnets and a quadrupole triplet to separate the electrons from the ion beam and to guide the electrons onto an electron detector. And then by setting the magnetic rigidity of the spectrometer, we can select 1 momentum of electrons that is guided onto the detector. Now the geometry is like this, that the angular acceptance is 2 pi for the azimuthal angle, and the electrons are emitted from 0 to 2.4 degrees that we can detect. And some kinematic considerations. So if the electrons are emitted into forward direction and we look at those electrons that travel with a velocity similar to the projectile velocity, if the electron has a very low energy compared to the projectile, we can see 4 pi of the electrons. Now, if the electron is much faster and is fast compared to the projectile, we can only see a small angle of the electrons. And this, later we will see, has a strong influence on the electron distribution which we observe. So there's a angular transformation, and it's important that we rotate the laboratory frame to the projectile frame by 180 degrees. So what do we measure? Here, this is the first process, the electron loss to continuum. The electron is ionized from the projectile. And we see this distribution. You see in the bottom the electron energy in the laboratory system. And on the top, you see always the electron energy in the projectile system. Of course, we have most of the electrons that have the same velocity as the projectile. 50 keV corresponds to the 90 MeV projectile energy. The theory you see is a fully relativistic calculation using Dirac wave function and first order perturbation for the interaction. Now it's calculated like this. The projectile is purely ionized by the nucleus of the target. So the nitrogen nucleus hits the projectile and an electron is emitted, and then you get a double differential distribution of the electrons that you have to convert from the projectile frame into the laboratory frame to get this distribution. The target electrons do not play a role in this calculation. And I want to stress that in the energy distribution in the projectile frame is almost constant within the measuring range that we studied. That means the cusp is really, in this case, formed by this transformation. As we have a beryllium-like projectile, it can be ionized either the L shell or the K shell. And of course, the probability of ionizing the K shell is much smaller. It's about 2%. But we did observe this. So in coincidence of the ionized projectile and the electron and the photon that is emitted after the decay, we can also, with very low statistics, see this process. We have this corresponding distribution in the projectile frame. Right. The details you can read in the paper. Then the second process we looked at is the electron capture to continuum. The electron is ionized from the target and is captured into the continuum of the projectile. We see a strong asymmetry of this cusp, and this is especially visible because of the high projectile charge that we use. Experimentally, this is challenging because we only see the electrons. We don't use a coincidence, so we have to subtract the other processes. And theoretically, this is challenging because it's a large momentum transfer process. So it's in principle, it requires a really two-center approach to calculate this. And a fully relativistic two-center approach for continuum electrons is, as far as I know, not yet available, but we use non-relativistic continuum distorted wave calculations or also impulse approximation calculation to reproduce this. For the CDW calculation, there's a poster tomorrow. So it's details you have in another paper. And then the third process, the most interesting, is the radiative electron capture to continuum. Here we detect the electron in coincidence with the photon. And in the electron distribution, you see totally opposite asymmetry of the other process. So you only see electrons that are faster than the projectile. And this you can, again, only explain if you look into the projectile system. Here, only the target electrons play a role. And the target electrons scatter off the heavy ion and lose part of its energy to emit a photon. And this is now really a Bremsstrahlung process. The electron scatters off, and according to energy conservation, the outgoing electron has a very low energy. Almost all energy is transferred into the photon, and that's why this is also called the high energy endpoint of Bremsstrahlung. There's a quite complex photon spectrum, which I don't have the time to explain now, but here you can see by selecting the coincidence with the electrons, the photons from the high energy endpoint. For a given angle of the photon that is emitted, you can then again calculate the electron distribution. And here you see that the electron is always emitted into the backward direction in the projectile frame. And then, as I showed, the transformation includes a rotation by 180 degrees. And then you can understand that the electrons in the projectile frame are always faster than the projectile after the collision. And this shape is also strongly influenced by the transformation, because in principle the the energy distribution is also constant within the measuring range, roughly. And then, since this is triple differential cross-sections, we have different photon angles, and we had 5 X-ray detectors, so we could measure the distribution of the electrons for 5 different X-ray angles, and then determine the photon angular distribution for a given electron energy. And it's roughly a sinus-square distribution with a slight deviation due to the fully relativistic treatment if you calculate this. So you can read this in another paper. That means, so this is, I can stress, this is one experiment where we observed 3 different processes, and for the specific collision system, all of these 3 processes contribute roughly equally. So in summary, we have successfully implemented a magnetic forward angle electron spectrometer in a heavy ion storage ring. And we have studied the 3 processes contributing to the electron cusp in collisions of the heaviest available projectile ions with a light atomic target. As an outlook, okay, and tomorrow there's a poster also. As an outlook, we are currently analyzing data for uranium-28+, so multi-electron projectile colliding with different gas targets. And there we observed experimentally that the asymmetry of the cusp strongly depends on the target that you use. And we are currently trying to understand this also in discussion with theoreticians. There's another poster about this tomorrow. And with this, I would like to thank all my colleagues and collaborators who contribute to this, many experimentalists and several theoreticians for different processes, and thank you for your attention.